Welcome to this presentation. It's on step paper 1 2001, the first question. Let me read the question. The points A, B and C lie on the sides of a square whose sides are 1 centimetre. No two points lie on the same side. Show that the length of at least one side of the triangle ABC must be less than or equal to root 6 minus root 2 centimetres. So this is a kind of geometric question, and I want to do it in two parts. I always want to do it back to front. I want to assume that the triangle is a certain shape and work out what its length of sides are, and then prove that the triangle has to be that shape. What do we mean by has to be here? Well, we're asked to show that the length of at least one side of the triangle must be less than or equal to root 6 minus root 2. So that means that no matter what triangle you try to fit in this square with the points on opposite sides or somewhere around on the square, then at least one side must be as big as this. So what we're trying to do is to find the maximum that the smallest side of one of these triangles can be. And it turns out, I'm going to show this in the second part, that triangle is an equilateral triangle where one of the corners coincides with the corner of the square. So this is equilateral triangle. I'll call the three sides x, and this is 60 degrees, and we're trying to find the length of this side. Now it turns out that that angle is 15 degrees, and this angle in here is also 15 degrees. And you can see that either just by symmetry, or else if you want to be a little bit more rigorous about it, you can look at two triangles. The triangle ABQ, which is this thin little triangle here, and the triangle ADR, which is this little triangle here, and you can show that they're congruent because the two sides x are equal because that's an equilateral triangle, and the two sides of the square are equal, that's AD and AB, and they've both got a right angle in them, so by RHS they're congruent, and therefore these two angles are equal, and together with 60 they make up 90 degrees, so each of them have to be 15 each. And that means that the cosine of 15 degrees is equal, if we look at the triangle here, ABQ is equal to AB over PQ, or AQ, and AB is equal to 1 because the side of the square is 1, and AQ is x because x, that's the side of the triangle we want to find, and a little bit of rearrangement shows us that x is equal to 1 over cosine of 15 degrees. And you might think, well, we're home and dry here. Just look up our calculator, what cosine 15 is, take the reciprocal, that'll be x. Unfortunately, this is a non-calculator paper, and what's more, they seem to want the answer in terms of the square roots. So we've got to find some way of working out what the cosine of 15 degrees is. Well, we know the cosine and indeed the sine of certain angles. We know 30 degrees, 45 degrees, 60 degrees, and 0 degrees, and 90 degrees, and multiples of these. We know, for example, that sine of 30 is a half, and cos of 30 is equal to root 3 over 2, and cos of 45, which is the same as sine of 45, is 1 over root 2, and you can prove this by looking at, for the 45 degrees, take an isosceles triangle, which has also got a right angle, and if you do Pythagoras with the sides 1, 1 and 2, you'll see that the cosine of that angle, which is 45 degrees, is 1 over root 2. And you can do something similar with take an equilateral triangle whose side is 2 and drop a perpendicular down to the side, then that's length 1, and this angle in here is 30 degrees, and by looking at that triangle with a little bit of Pythagoras you can work out those. And this is going to help us because the cosine of 15 degrees is equal to the cosine of, let's say, 45 degrees minus 30 degrees. And I can use a formula. The cosine of a minus b is equal to the cosine of a cosine of b. I've got to be careful here, plus the sine of a sine of b. And that's a standard formula, and you really need to know that formula to solve the problem this way. So here we have a is 45 degrees and b is 30 degrees. So I want to fill those in here. Cosine of 45 degrees is 1 over root 2. Cosine of 30 degrees is root 3 over 2. Cosine, or rather sine of 45 degrees is 1 over root 2. And sine of 30 degrees is 1 over 2. And this equals 2. We can make a common denominator of 2 root 2. 2 root 2. And then we've got a root 3 plus 1. And that's what cosine of 15 degrees equals to. And x, therefore, is equal to, well, the reciprocal of that, which is 2 root 2 over root 3 plus 1, which isn't exactly the same as what we're asked for, but maybe we can make it the same. If we get rid of the denominator, or the square roots in the denominator, and use this by a standard technique of multiplying top and bottom by the same thing. I'm going to multiply by root 3 minus 1 over root 3 minus 1. So we haven't changed x by doing that, and that will turn out to be, well, let's see. Now in the bottom we've root 3 plus 1 on root 3 minus 1. It's the difference of two squareds. A plus b on a minus b. It's the same as a squared minus b squared. A squared in this case is 3, and b squared in this case is 1. So it's 3 minus 1. And on the top it's 2 root 2 times root 3. So I'll write that as 2 root 2 root 3 minus 2 root 2. I've got the 2 root 2 by multiplying 2 root 2 here by minus 1. And we're nearly there. We can put the denominator is just 2. 3 minus 1 is 2 over 2. Now root 2 root 3 is the same as root 6 minus 2 root 2. We'll just leave that as the same. Now we can divide through by 2, and we get root 6 minus root 2, which is what we have to prove. So that completes the second part.